Welcome back, everybody. In this video with the PIC 18F4550, we're going to write a program to control 4 LEDs with timers and interrupts rather than delays. You might be wondering, why not just use delays for everything as in the previous video? Well, here's why. Let's say you have a really simple microcontroller project that's only doing one thing at a time. Now, thing to do could be just about anything that you could think of a microcontroller doing. For example, reading a switch, reading a sensor, updating a display, communicating over a bus, commanding a motor, etc. So if you have this situation, for example, let's say thing to do is updating a motor position every 1/10 of a second. So you could update the motor position, have a delay loop to pause for a 1/10 of a second, update the motor position again, same delay loop to pause for a 1/10 of a second, and so on. So this would work for only doing one thing at a time, simply using delays. But almost any real-world microcontroller project, your microcontroller isn't going to have just one thing to do. For example, let's say you have 4 things to do. Thing to do 0, 1, 2, and 3. Well, in this case, for example, say thing to do 0 was updating a motor position every 1/10 of a second, and thing to do 1 was updating a motor position, let's say every 1/4 of a second. So if you command thing to do 1 motor position and then you wait a 1/4 of a second in a delay loop, that whole time thing to do 0 can't be updated, and neither could thing to do 2 or 3. So clearly that strategy isn't going to work. So for multitasking, what we have to do is use timers and interrupts. So for our simple example program today, we're simply going to blink LEDs for our 4 tasks, but as in the previous slide, these, instead of LEDs here, these could be just about any functionality that a microcontroller could perform. So before we get to writing code today, let's take a quick look at the 18F4550 datasheet and some of the information on timers and interrupts that's provided. So if we scroll down on the left to section 9, interrupts, this is going to summarize our interrupt registers for us. USB interrupts, we'll get back to that in a future video, but some of these other registers we're going to set today. The interrupt control register, peripheral interrupt request register, peripheral interrupt enable register, and peripheral interrupt priority register. As well as the interrupt registers, each of the 4 timers, the PIC 18F4550 has 4 timers, by the way, timers 0, 1, 2, and 3. And each of them has their own section in the data sheet here. So the general strategy with these timers is, for example, let's use timer 0. Each timer will have a sort of a main control register, and that's going to be called T0con in the case of timer 0. In the case of timer 1, it's called T1con, and so on. And then at the end of the section, for each timer, there's this nice presentation where here all the registers associated with that timer, so for example, in this case, timer 0 are summarized. So here we have timer 0 low, timer 0 high, intcon, and intcon 2, and then T0con, again, that's the main configuration register specific to timer 0, and then also tris A. So the idea here is timer 0 low and timer 0 high. Now these registers, these counters, timers and counters rather, can be either 8 or 16-bit. In the case of timer 0, you have the choice of it being 8 or 16-bit. For the other 3 timers, they either are 8 or 16, but again, we'll get to that later. So here's how the idea works. You're going to set timer 0 to be either 8-bit or 16-bit, and then when it starts counting, it starts out with these registers at all 0. And when they overflow, that's when the interrupt occurs. So for example, 2 to the 16th is 65,536. So these 2 registers will be incremented 65,536 times. Once they hit that amount and they overflow back to 0, that's when the interrupt is signaled. Now when that happens, the timer 0 interrupt flag is going to be set. So when we go into our interrupt routine, we can check which interrupt flag is set. If we see it's timer 0 IF, then we know that the timer 0 is the timer that just rolled over, and we can handle the interrupt from there. So before we actually get to writing all this in code, let's take a quick look at a comparison of the 4 timers, and also how we're going to set the timing for each of the 4 timers. So let's take a look at a quick chart here summarizing some of the differences between the 4 timers in the 18F4550. So we're going to look at the number of bits in the timer's counter registers, and then also the prescaler and postscaler options. I'll explain those in a moment. And then in some cases, it's advantageous to use an external source to increment the timer's counter registers. We're actually not going to do that in our program today, but here's which ones can and can't be incremented that way for your reference if need be. So the first thing that definitely we want to consider in our calculations is the timer we're working with is an 8-bit or 16-bit. Timer 0, you can choose 8-bit or 16. Timer 1 is always 16, timer 2 is always 8, timer 3 is always 16. The next are prescaler and postscaler. Now the clock in modern microcontrollers is so fast that, for example, if you're working with USB communication, you have a 48 megahertz USB clock, and then you also feed the same clock speed into your CPU, which we're not going to do that today. We're going to use the internal clock, which is only 1 megahertz. But anyhow, suppose you're using a 48 megahertz clock. A 16-bit timer might sound like a lot to have to go through 65,000 cycles before it increments, but actually it's really not. It's a pretty short amount of time when you're talking about many millions of clock cycles per second. So what the prescalers are and postscalers are is they multiply out the amount of time that it takes the timer to roll over. So for example, if you have 2 to the 16th, which is 65,536, but then you use the timer 1 prescaler of 8, then you would multiply the amount of time that it would take to go 65,536 counts times 8, and it's going to take 8 times that long. With timer 2, you even have a postscaler option. So for example, if you did 2 to the 8th, which of course is 256, so if you did that, that would be a very short amount of time. But if you do 256 times 16 times 16, that's long enough that maybe that would be more useful in certain situations. Timer 0 does not have a postscaler option, but it has an especially large prescaler option, which can be very handy. So now that we've gone over some of the differences in the timers, let's actually break out a calculation of how we're going to achieve some desired time so that we can blink some LEDs, have the blink fast enough that we're not waiting for the LED to blink, but at the same time slow enough our eyes can still perceive the blinking. Okay, so far we've gone over some kind of abstract topics. Let's actually go through the calculations for timers 0, 1, 2, and 3 to figure our delays. Hopefully that'll be a little bit more concrete, and then we can go to writing our program from there. So to make sure that we don't have our timers going too fast, we're going to use the 1 megahertz CPU internal clock, and we can achieve the 1 megahertz CPU speed by simply leaving the OSCON register at the default. And also bear in mind that the 18F4550 uses 4 cycles per 1 instruction. So for timer 0, we have a clock speed of 1,000,000 cycles per 1 second. If we multiply that by 1 instruction over 4 cycles, then of course cycles crosses out, and we have 250,000 instructions per second. So what we're going to do is we're going to use the timer 0 256 prescaler. So if we do 250,000 instructions per second divided by the 256 prescaler, that gives us 976.56 timer 0 increments per second. Now we're going to divide that by 2 to the 8th minus 30. Where do we get these numbers? Well, the 2 to the 8th is because the timer 0, we're going to use the 8-bit timer option. Again, there's an 8-bit or 16-bit option for timer 0. We're going to use the 8-bit option. And the minus 30 is because timer 0's counter register, we're actually going to start it out at 30. So it's going to count from 0 until 255 and then overflow and signal the interrupt, rather than counting from 0 to 255 and then overflow. And really the only reason for this is that it's adding this 30 in here is going to slightly offset the timing of timer 0 versus the other 3 timers, so that the LEDs won't seem to be synchronized in their blinking. They'll all be blinking at different times, so that we can see that our process is truly multitasking rather than something that's just achieved with delays. So if we divide out 976.56 by 2 to the 8th minus 30, we'll get 4.321 hertz. And I have hertz in quotes here because it's not really clock cycles hertz. This hertz here means the number of times per second that timer 0 will roll over. So if we invert this here, if we do 1 divided by 4.321, then we get this 0.2314 seconds. So in other words, the timer 0 interrupt will occur every 0.2314 seconds. So we'll turn the LED on, and then 0.2314 seconds will pass. Then we'll turn the LED off. Then 0.2314 seconds will pass, and so on. And that process will keep repeating. So that's our timing for timer 0. Okay, so timer 0 was actually the most complicated calculation that we're going to do. Hopefully after having seen the first calculation, the remaining 3 will kind of seem easier. So for timer 1, we're going to start with the same 1,000,000 cycles per 1 second on our clock, and then we're going to multiply that by 1 instruction over 4 cycles. Again, cycles crosses out, and we're left with 250,000 instructions per second. We'll simply use the prescaler of 1 for timer 1. So 250,000 divided by 1 is still going to equal 250,000. Then we're going to divide by 16 because timer 1 is a 16-bit counter. So that's going to give us 3.815 hertz. Again, hertz meaning the number of times per second that timer 1 is going to roll over. So if we do 1 divided by 3.815, that's going to tell us that timer 1 interrupt will occur every 0.2621 seconds. So now let's take a look at our timer 2 calculation. So timer 2 is different than timer 1 in 3 ways. One way is that timer 2 is 8 bits, whereas timer 1 was 16 bits. And another difference is that in the case of timer 2, we have both the prescaler and the postscaler option. The third difference for timer 2 versus timer 1, and also how timer 2 is different than timer 0, is this period register here. And what this is all about is that for timers 0, 1, and 3, the timer's counter starts at 0, or if you assign it to something higher than 0 to begin with, like for example, we're going to assign timer 0's counter to 30. But in any case, timer 0, 1, and 3 start at either 0 or what you assign them to, and then they continue to count up until they overflow the maximum number that can fit in their counter's registers, again, be that either 8-bit or 16-bit registers. Timer 2 is different. Timer 2 starts counting at 0, or whatever you assign it to, if it's something other than 0, and then it counts, but it doesn't necessarily overflow its 8-bit counting register. It goes until it gets to the value set in this timer 2 period register. So for example, if timer 2 starts at 0, and you set period register to 200, then timer 2 is going to count from 0 to 200, and then it's going to throw its interrupt. And then it's going to count from 0 to 200 again, throw its interrupt again, and so on. So it doesn't count up to the maximum it can fit in 8 bits. It counts up specifically to what you set this period register value to be. So here's how our timer 2 calculation is going to work out. It's going to start the same as the others. Million clock cycles per 1 second times 1 instruction over 4 cycles gives us 250,000 instructions per second. And we'll use the prescaler of 16 that divides out to 15,625. Then we'll divide that by the postscaler of 16 that divides out to 976.56. Then we'll divide that not by 2 to the 8th, but by 200, because we're going to set the period register to 200. So that's going to give us 4.883 times per second that timer 2 is going to roll over. So if we do 1 divided by that 4.883, that tells us that the timer 2 interrupt will occur every 0.2048 seconds. So after looking at the first 3 timers, timer 3 should be pretty easy. So we're going to start out with our same million cycles per second times 1 instruction over 4 cycles. Cycles cross out, so we have 250,000 instructions per second. And we'll divide that by the prescaler value we'll set to 2. So that's going to give us 125,000. We're going to divide that by 2 to the 16th because timer 3's counting registers are 16 bits. And that's going to give us 1.907 times per second that timer 3 will roll over. So if we do 1 divided by the 1.907, that's going to tell us that timer 3 will roll over and throw its interrupt every 0.5243 seconds. So here's going to be our circuit diagram for today. Again, this is about as simple as it gets with the 18F4550. We simply have the programming header, power and ground on both sides, 1 smoothing cap, and then on RB 0, 1, 2, and 3, we're going to have 4 LEDs and resistors to match. So please go ahead and breadboard the circuit if you haven't already, and let's go ahead and fire up MPLAB. Put our name in, and now we're ready to start coding. So rather than entering all our chip configuration stuff from scratch, we can simply navigate to our Blink internal clock program, open up the C file in Notepad, and copy and paste the chip config settings, since we're using the same internal clock as the Blink internal clock program in the previous tutorial. And so that part's already done. Now we're ready to move on to our includes. So next we're going to declare 4 global variables to keep track of the state of each of the 4 LEDs. And later on, we're going to write 4 functions, one for each of the LEDs, to flip them. So in other words, if the LED's on, turn it off. If it's off, turn it on. Now we're ready for our function prototypes. So we're going to have 6 function prototypes in this program, and 4 of them are going to be the LED flip functions, but 2 of them, if you haven't worked with interrupts before, are going to be a little bit new, and these are especially important. So let's take a look at those. We're going to have void, high ISR, and that's going to be void. And then we're going to have void your high priority interrupt code. And that's also going to be void. Let's quickly write down our 4 prototypes for the LED flip functions, and then we'll get back to writing the interrupt functions. Okay, so now we're ready to get to our interrupt functions. So we're only going to actually have one interrupt function that's going to handle our interrupts, but you'll notice we declared 2 function prototypes. What's the reason for that? Well, the reason is that the way that the hardware in the 18F4550 works out and the way that the microchip C compiler interacts with it, we have to call, or write I should say, the first function high ISR, and that's where the hardware is actually going to bring it to. Then we're going to have a go-to statement in that function that's going to go to our actual function that's going to meaningfully do the interrupt. Now the reason for this is that the high interrupt function has to be located at a certain memory address. So here's how all that's going to work out. And we have to assign this to address 8. And in case you're wondering where this number comes from, if we reference the 18F4550 datasheet, section on interrupts, we'll find here that the high priority interrupt vector has to be at address 8 and the low priority interrupt vector has to be at address 18, always. That's a physical part of the hardware of the 18F4550 chip. But the thing is, if we actually left it at that address, we wouldn't have enough room because other stuff has to go after that to actually put our entire function in there. So here's how we're going to handle that. We're going to write the rest of the function here, void high ISR, void, and then we're going to put an inline assembly statement here, ASM go to your high priority interrupt code. Let's simply copy and paste that from up here. And then we need underscore end ASM to end that line. Now because this code is going to be placed at this certain address here because of the pragma code statement, at the end of that function we definitely want to put pound pragma code, so that anything else we put after that is going to return it back to usual. So now we're ready to write our interrupt routine. And now we can actually write our interrupt function. And again, because we want to go back to regular code after that, we want to put pragma code. So once we jump into the interrupt function, what do we actually need to do? Well, for each of the 4 potential interrupts, we're going to assign all 4 interrupts to be high priority to make the program relatively simple. You can assign interrupts to low priority or high priority, but for this program we'll just make them all high, so that way we're only writing one interrupt function. So when we come into the interrupt function, how do we know which interrupt just occurred? Well, the answer is that there's a bit in various registers, and we'll get to which registers in a moment. But for each timer there's a bit in interrupt flag bit, and if that's equals 1 when the function starts, then it's that interrupt that was thrown. So for example, if we type intcon bits dot tmr0 if, That's short for timer 0 interrupt flag. So if that equals 1, that tells us that the timer 0 interrupt just occurred. And we'll come back and write the rest of that function later. So then for each of the other 3 timers, we're going to have a very similar statement. So the first thing that we're going to need to do in each of the if statements is we're going to have to clear the interrupt flag. If we leave it at 1, then we won't be able to have the interrupt signal again the next time the counter's register overflows. So let's take care of that first. So here we're going to do incon bits dot timer 0 input flag is going to be assigned 0. Next we're going to call the flip led function, and again we'll write those 4 functions at the end. But in a program that was doing something like reading a sensor, updating a motor position, etc., you would put that command here instead. And as we mentioned in the timing calculations earlier, in the case of timer 0, simply to make it so it wasn't in sync with any of the others, so they're all blinking at a different rate, we're going to set timer 0's counter register, that's TMR 0L to 30. So that way timer 0 is going to count from 30 to 255 and then overflow, rather than from 0 to 255 and then overflow, just to make the timing different from the others. So now we're basically going to go ahead and do the same thing for the other 3 timers, only we're not going to need that timer 0 low assignment equivalent statement. So that completes our interrupt function. So now we're ready to write main. So the first thing that we're going to do in main, as a precaution, until we've actually configured the timers, let's turn them all off to make sure they don't start when we're not ready for it. The next thing that we're going to do is we're going to set the ADCON 1 bits, PCFG 0, 1, 2, and 3 to 1 to make sure that all of the pins on our chip that are potentially analog pins or digital, we're going to set them all to digital. Next we're going to configure RB 3, 2, 1, and 0, which of course are the pins that our LEDs are on. We're going to configure those to be output pins and also initiate them to off. The next thing that we're going to do is we're going to set the RCON IPEN bit to 1, and what that's going to do is that's going to enable priority levels on interrupts, so in other words high versus low. And then after that we're going to set the incon bits GIE or GIH bit to 1, and that's going to enable high priority interrupts. So now we're ready to configure each of our 4 timer registers. So before we go any further with that, let's quickly take another glance at the 18F4550 datasheet. So some of the registers we've configured already, for example, RCON and INCON. The registers that apply to all of the timers we're generally going to find in section 9 here, interrupts. So here's RCON and INCON, and if we look on the contents here on the left, there's RCON section 9.6. You can look what each of the bits do individually. And here's INCON section 9.2. So as we're going through each of the timers, 0, 1, 2, and 3, you probably should reference the applicable section 11, 12, 13, or 14, And here we can see what the bits are, for example, timer 0, control register, and so on. So now we're ready to configure timer 0. So what we're going to do is we're going to set itcon bits dot timer 0 interrupt enable to 1, and that's going to enable the timer 0 overflow interrupt. Next we're going to set itcon 2 bits dot timer 0 interrupt priority to 1. That's going to set timer 0 overflow interrupt to high priority. Next we're going to set T0 con bits, specifically the T0 8-bit to 1, and what that's going to do is we're going to use timer 0 as an 8-bit timer. If we set this to 0, that would make it the 16-bit option. Next we're going to set the timer 0 CS bit to 0. That's going to use the internal clock to increment timer 0. And then we're going to set the PSA bit to 0. That's going to use a prescaler with timer 0, and again in the next set of instructions we'll actually set the prescaler amount. Now we're ready to set our prescaler amount for timer 0, which we're going to set to 1 to 256. So again, if you're wondering where any of these particular bit settings come from, they're all in the datasheet. For example, the T0 PS0, 1, and 2 bits to set the timer 0 prescale to 256. If we go to section 11 and we look at register T0 con, we'll find that up here for register T0 con, we can simply set the T0 PS2, 1, and 0 bits as follows here to achieve our desired prescale. So for example, we desired the 1 to 256 prescale value from our calculations earlier, so we're going to set those 3 bits to 111. And any of these other bits, and also the other matching registers for the other timers, you can simply look the values up in the same manner. So I think I'll fast forward through the timer 1, 2, and 3 configuration, since they're very similar to timer 0, and of course you can look up the details in the datasheet as you prefer. So here's our timer 1 configuration settings. Let's take a quick look at those. So with timer 0, we did the timer 0 interrupt enable to 1 and timer 0 interrupt priority to 1 to indicate high priority. So we're going to do the same thing with timer 1. Timer 1 interrupt enables 1, timer 1 interrupt priority is 1, and then we're going to set the prescale. That's T1 CK PS 1 and 0 bits in the T1 con register, so we're going to set those to simply 0 and 0 to achieve a prescale of 1 to 1. And then we're also going to set this T01 OSC EN bit and TMR1 CS to 0 and 0. That's going to turn off the separate oscillator that's internal to timer 1, and that's also going to use the internal clock to increment timer run rather than a signal from an external pin. And that completes our configuration for timer 1. Now let's move on to configuring timer 2. So here's our timer 2 configuration. This looks a little different from the previous two in the sense that now, in addition to the prescale value, which we're going to set to 1 to 16 with these 2 bits here, we also have a postscale value to set, which we're also going to set to 1 to 16 with these 4 bits here. And we're also going to set the period register. So recall, this is the amount that the timer counts up to. So in other words, instead of going from 0 to 255 and rolling over, it's going to go from 0 to 200 and then flag its interrupt. 0 to 200 again, flag its interrupt again, and so on. And then we're also going to make sure to enable the interrupt and set the priority to high. And that completes the timer 2 configuration. Now let's take a look at our timer 3 configuration. So as with the other timers, we're going to set interrupt enable to 1 and interrupt priority to 1, signaling a high interrupt. And we only have a prescale value to set here now, so we're going to set that to 1 to 2 with these two bits here, T3, CK, PS 0 and 1, setting those to 0 and 1 respectively. And then we're also going to set the timer 3 clock source bit to 0, and that will indicate to use the internal clock to increment timer 3, and that completes our timer 3 configuration. So now all that's left to do is turn our 4 timers on and then have an endless while loop that will allow the timers to do what they're going to do. So now at the end we're going to come back and we're going to write the 4 functions to flip the LEDs 0, 1, 2, and 3 that the interrupt routine from earlier called. So there's our first LED flip function, and I'll fast forward the other 3 since they're basically going to be exactly the same as this function, only instead of LED 0 it's going to be LEDs 1, 2, and 3. And now we've got all 4 of our LED flip functions in place. Let's go ahead and compile. And whoops, I must have made a typo somewhere. Darn, that should be int con bits. And let's try that again. And there we go. Now we're ready to load our program and test it. Alright, so here we've got our breadboarded circuit and our PIC-Kit 2 connected. And we've opened our PIC-Kit 2 software, so let's go ahead and load the hex file. So we're looking for 18F4550 timer and interrupt example 1.1. And there's our hex file compiled just a few moments ago. Imported. Right. I'll zoom in while that's writing. And go ahead and turn the power on. And there we have it. There's our 4 different LEDs being blinked by 4 different timers, and no delay loops are involved, so we've truly achieved multitasking with the 18F4550. Congratulations! You now know how to perform multitasking with the PIC 18F4550 via timers and interrupts. In upcoming videos, we're going to take a look at a motor controller example, an updated version of the USB demo board, and also a USB motor controller example. See everybody next time.